Hi, everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And we seem to have lots of questions saved up or queued up here. Let me see. All right, let's start off with one from Mikhail. The question was, is there any experiment in computation similar to the Miller-Urey experiment in origins of life? Well, so first of all, let me say a little bit about the Miller-Urey experiment, which was in, I think, the early 1950s. So the question is, how did life originate on Earth? Life has a lot of complicated features. It has DNA, it has proteins, it has lots of complicated mechanisms, and so on. Question is, how did all that stuff originate? And how do you go from sort of inorganic chemicals, and I say inorganic in quotes because when you study chemistry, there's this field of so-called organic chemistry, which basically means chemistry of bigger molecules that have carbon and hydrogen and oxygen and things like that in them, as opposed to smaller molecules with more exotic kinds of elements in them. It doesn't mean organic. You might think means relating to life, but there the word organic just means with those particular carbon and so on related elements, which are the most common elements that show up in life. But it isn't the case that all things with carbon and hydrogen and oxygen have to do with life. I mean, something like that there are plenty of chemicals, whether it's carbon dioxide or whether it's plastics that are still hydrocarbons, and made from carbon and hydrogen and so on, and don't have anything directly to do with life. So, but one of the questions is, how do you go from just a random collection of chemicals to something like a living system? And that's been complicated to answer, and there are probably many steps. And one of the things that was done in the 1950s was to ask the question, if you just pour random chemicals together and just sort of heat them up a bit and stir them around, can you start getting more complicated molecules of the kind that one might see in living systems? One wouldn't expect a whole giant DNA molecule with 6 billion base pairs like we have to be sort of to come out of just stirring things around for a few minutes. But you might expect some molecules that have, I don't know, 20, 30, 50 atoms in them to be things that would somehow spontaneously form as a result of just chemical reactions without any kind of long story of biological evolution or anything like that. And indeed, that was exactly what was discovered. You just throw all these chemicals together, and some of them start combining, and you pretty soon you're getting slightly larger molecules that are slightly reminiscent of the kinds of molecules that show up in living systems. Now, there are many other places where you get these sort of slightly longer molecules, like, for example, in interstellar space, there are molecules that can be quite big that are formed in very different ways. The molecules are formed in chemical reactions on the Earth. So a lot of places where a place where it's sort of easy to have chemical reactions is in the sort of liquid phase of materials, because it's a place where the molecules are dense enough that they are often hitting each other, but yet they're not so dense that they're sort of all packed in and forming a rigid array like in a solid, where two sort of different molecules can't ever find each other. So the liquid phase is the place where chemical reactions are kind of at their best, so to speak. And that's kind of why, in things like airport security, it's like worrying about how much volume of liquid one might have is a significant thing, because if you want a chemical reaction that might produce some explosion or some other bad thing to happen, it's probably going to be something that is achieved by mixing liquid chemicals together in the liquid phase. So in any case, in the early Earth, for example, no doubt the chemical reactions which eventually led to life were liquid phase chemical reactions. In interstellar space, there aren't liquids, but instead there are very dilute individual molecules. And so the way that larger molecules get formed in interstellar space is rather different. It's usually the sort of individual collision of molecules with each other, not the kind of continual jostling around that happens in a liquid. But nevertheless, even in interstellar space, some slightly complicated molecules can be formed. And when one's looking, for example, at the atmospheres of other planets, or even exoplanets, planets around other stars, sometimes you can get a little bit of information about what might be in the. Well, I don't think we yet have that information, but it will be possible to get the information about what kinds of chemicals exist in the atmospheres of exoplanets, just by looking at light coming from those exoplanets, possibly light that when the planet goes in front of their star, maybe there'll be things absorbed as that light goes through the atmosphere of the planet and so on. Things like that will potentially allow one to get information about what kinds of chemicals exist in the atmospheres of those planets. So then the question is, what kinds of, are there molecules there where we say, aha, that's a molecule that corresponds to something to do with life? And there was a recent thing on Venus, actually, that in the clouds of Venus, there were phosphines that seemed like they were being observed. And people were like, well, phosphines are kind of complicated molecules, and they're kind of a little bit like the molecules that are building blocks for life. And maybe that's a sign that one should be looking on Venus for possible life, maybe in the clouds, above the surface of Venus. But in any case, that's so kind of what happened in the Miller-Urey experiment was this kind of a liquid phase thing where you're sort of putting molecules together and getting somewhat bigger molecules. Okay, so a question that might arise is, well, how do you go all the way to actually get life as it has formed on Earth? And it's not clear what the essential feature of life is, but for example, self-reproduction is an important feature. And there are all kinds of theories about types of materials like clays, for example, which are solids, but they have a lot of sort of repeating, a lot of different elements that can exist in them. And maybe there are ways that they could have been used as sort of templates for creating molecules that would then be repeated sort of from generation to generation, if that was an important thing in the origin of life. But we don't know the details of how life originated on Earth. But one thing that one does get information from is throw a bunch of chemicals together, see what you get. Now, an interesting feature is most of the time when people are thinking about making chemicals, they are not thinking about what is sometimes in the business of chemistry called one-pot synthesis. You just sort of throw everything in a pot and see what happens. They're rather thinking of how do we very carefully do this reaction, that reaction, that reaction to end up with a particular product. Like we're trying to make a particular industrial chemical, or we're trying to make a particular drug. How do we arrange, how do we go from the kinds of components that we can just sort of buy off the shelf from a chemical supply company, whether it's, I don't know, ammonia, or whether it's some other chemical, put water in, put this in, put things that are sort of readily available chemicals that can be got from just a chemical supply company. How do you go from the chemicals you can buy from a chemical supply company to manufacturing that amazingly useful, drug of some kind? And usually what happens is people invent this whole series of moves that you can make. It's like, okay, pour these two chemicals together and heat them up to this temperature. Okay, then for this amount of time. Then, okay, then take that result, add this chemical, heat it up in this way, do this, do that, and so on. And usually in the chemical syntheses that are done today, there may be 20 or 30 steps that you go through of trying to sort of add this, heat that, do this, etc., to end up with the particular product you want. And that kind of synthesis, one of the big issues is what is the yield of that process? That is, given the amount of material you put in, what fraction of the stuff that comes out is actually the chemical you want? And that yield is gradually tweakable. You can use catalysts, for example, which are materials or chemicals which are not directly going to contribute to the end product, but they typically might even be solids where they have a sort of a shape on their surface where molecules that are going to be relevant to the reaction, like collecting in these little crevices, for example, in a surface, and they end up collecting in those crevices in such a way that they align themselves so that they'll react in a particular fashion or something like that. There's sort of a whole complicated art of building catalysts that have the right sort of surface structure or the right chemical properties and so on to speed up reactions. In biology, we have a class of catalysts called enzymes that are incredibly efficient at speeding up biological reactions. Without enzymes, biology really wouldn't work the way it does. They speed things up by factors of billions and things like this. They're often very sensitive to the temperature at which they operate, which is why sort of life exists, and we tend to exist only at a pretty narrow range of temperatures. I think anyway. So the question here of how does one get the whole sort of network that corresponds to the chemistry of life? We don't know the answer. We know that there are many kinds of networks of chemicals that achieve things. Like, for example, metabolism is a particular network of different kinds of chemicals being involved that all contribute to being able to take energy, take food, turn it into energy, things like this. There's some theories about how when you throw different chemicals together, there'll be sort of a tendency to get things like autocatalytic sets, things where there are sort of sequences of chemicals that sort of catalyze, where one chemical sort of automatically catalyzes other reactions, and where you get this sort of pattern of chemicals affecting other chemicals and so on. Now, that kind of segues into something more computational, because it always used to be the case, when I was younger at least, that you would see, if you went into sort of a biology lab or something, you'd see these giant wall charts, and they would have titles like, the metabolic pathways of the cell, or various kinds of signaling pathways and so on. And they'd be full of little signs for different kinds of chemicals and arrows saying this chemical reacts with that one to produce that, and so on. I think those wall charts have gone out of fashion, possibly because what's now known about how biology works is so complicated, it wouldn't really fit on a very good wall chart. But the idea of this kind of whole network of reactions is one that does seem to be characteristic of biology. And there's sort of a question of, can you capture the essence of that kind of network of reactions in a completely different way than life on Earth does it? Can you make something where the essence of what's going on is this network that has these various loops and various transitions and things like this, and do it with completely different chemicals? And is that the essence of what life is doing? We don't know for sure. I think that things that I've actually looked at even fairly recently have been along the lines of thinking about how you make sort of idealized chemistry that has that sort of captures these computational aspects of chemical A affects B, affects C, affects A, affects D, affects whatever, where the A, B, C, D, E doesn't really matter what they are. What matters is just something's affecting something, it's affecting something. So one of the things I've actually looked at quite a bit recently is the question of, instead of emphasizing doing chemical synthesis where you have one product as the output, think about the possibility that you can have something where there's a whole network of possible chemical reactions, producing all these different things. And you're using all these different things, and you're eventually building up this kind of giant giant network of all these different reactions, rather than the thing where you're trying to synthesize one particular thing. And I suspect that life is much more the use all these reactions and have them all flow in different ways, rather than the produce one thing. When we think about doing things with computers, for example, we tend to think, it tends to be a lot easier for us to think about do this, then do this, then do this. Or maybe if we're thinking about things in terms of functional programming, apply this function, then this function, then this function, apply that function to this structure, et cetera, et cetera, et cetera. The idea that there are many things happening in parallel that are all sort of independently happening, and then there'll be sort of somehow, as things go on, there'll be more independent things happening, but eventually, every so often, one will get the thing one wants. That way of thinking about how things work computationally is one that we're much less able to do. It happens to be, from what we know now from our sort of project in fundamental physics, it happens to be that the universe works that way. If you look at the different parts of space, sort of space is, in our models, consists of these sort of independent atoms of space, these independent discrete points, maybe 10 to the 400 of them in our universe, huge number of them in our universe. And the way that sort of the universe progresses through time is by these various atoms of space. They're each connected to other atoms of space, and that whole pattern of connectivity is getting continuously updated. Space is kind of getting continuously refreshed. Every point in space is getting continuously refreshed. And but that's happening all in parallel. All these different points in space are all doing that in parallel. It's not something where you can say, let's look at this thing, then this thing, then this thing, and so on. But there's kind of a big thing in our models of physics. There's this property of causal invariance that means that even though all these things are happening independently and in parallel, and it's all very complicated, it's possible, if you look at the right feature of the system, to see simple things that happen in the system. Even though a lot of what happens in the system is extremely complicated, there's sort of a slice of what's happening that's very simple. And it turns out one of the big things from our physics project is this, one of the slices that comes out is relativity. Einstein's theory of relativity is sort of a slice of what you can make sense of in the sort of evolution of the structure of space. Much of what happens in the evolution of structure of space you can't make sense of. It's computationally irreducible and so on, but some of it you can. What I've actually realized recently is that a lot of the story of what consciousness is and how sort of consciousness differs from sort of all the stuff that exists in the universe is the fact that consciousness is a story of sort of having a single thread of experience. We don't have sort of this experience as if we're all these separate atoms of space. We have a kind of coherent thread of experience of this happens, then this happens, then this happens, and so on. And it's not obvious that we can form a consistent view of what's happening in the world in terms of this happens, then this happens, then this happens. And it's a feature of this thing called causal invariance that means that even though all these different places in space are getting updated separately, it's still possible for us as the sort of consciousness that has a sort of single thread of a perception of what's going on in the universe to form a view of that is consistent, both self-consistent for ourselves and consistent kind of one person, one consciousness to another. And that's kind of a way of understanding sort of the difference between what happens just sort of in nature, all these sort of things happening in parallel, and our perception of it, our sort of consciousness version of what's going on, which is much more this kind of sequentialized version of what's happening. And that means that's sort of the fundamental reason why when we think about doing programming, for example, where many things are happening in parallel, where that's fundamentally quite difficult for us to understand, because the whole story of our kind of, consciousness and our experience and so on is all based on this sort of one experience going through time, so to speak, rather than this sort of whole parallel collection of different experiences. So when it comes to thinking about something like chemistry or biology, for that matter, we have a great tendency to try to reduce it to the one thing happening through time. And so, if you look at a medical textbook, for example, you'll see all these charts that say, this happens, then this happens, then this happens, this affects that, affects that. They're very sequentialized, so to speak. The true story of biology is likely not like that. It's likely something which has many different things happening kind of in parallel, and it's sort of building up this graph of interactions that somehow achieves the purposes it needs to achieve, but it does it in a way that is actually fairly hard for us to understand. And I think we kind of need a bit of a new paradigm for thinking about things, about sort of this distributed parallel computation, and that if we have that paradigm, we may start to understand a whole bunch more about how biology actually works. And if we're interested in things like the origin of life, it's important to understand what is the essence of how life on Earth actually works. I think that what we're about to see is kind of a fairly exciting way of importing things that we've learned from the last 100 years or so of physics. A lot of powerful things have happened in physics in the last 100 years, to import a bunch of those ideas into biology, basically, to understand more about the sort of very parallel kinds of things that are happening in the space of chemicals instead of the space of physical space of all these atoms of space, the space of possible chemical species, the space of possible different chemical compounds and how they react. So it's something I've been actually currently curious about. Now, you can ask the question of whether these kinds of processes that lead to sort of a lifelike thing being produced. First question is, what is a lifelike thing? And this has been sort of a mysterious story for the last few thousand years of, what is life really? Is there some, magic spark that makes something alive versus not alive? And people have these various definitions. The one in antiquity was, if it moves itself, then it's alive. That was a common one. And, eventually one had steam engines and things like that, and that wasn't a viable definition. There were definitions like it has certain kinds of chemicals in it, but then we learned how to synthesize those chemicals. So that wasn't a definition either. Maybe it has certain properties with respect to entropy and thermodynamics and so on, but we could synthesize things that we could create systems that had those properties as well. Or another one that was quite big is it has self-reproduction. It makes copies of itself. And but of course, people will say, well, at some level, fire, when it spreads, is sort of making a copy of itself. But more explicitly, when you have malware on computers, it's very common for computer worms, computer viruses to make copies of themselves, albeit in a sort of virtual world. So that's not a sort of unique definition about life. And what we realize in the end is that life as we know it on Earth is very easy to define, because all life on Earth has extremely similar sort of chemical processes going on. It's got RNA, most of it has DNA, it has proteins, it has cell walls that work in the same way. It has a tremendous amount of detail that's the same, presumably because it's derived from the same essentially common ancestor in the history of life on Earth. And so life on Earth is very easy to recognize. Life in the abstract is not clear what it means. I have long believed that life in the abstract is really just a story of sophisticated computation, that as soon as you're doing something that is complicated, it is life in the abstract, so to speak. It is not life in the specific of life on Earth with DNA and so on, but it is life, it is perfectly lifelike, so to speak, in the abstract. And it's a challenge when spacecraft go to Mars, for example. It's always a challenge of how do you tell if there's life there? And I remember when I was a kid and the first Mars landers were landing there were a whole collection of experiments about, could you tell if the Martian soil was alive? And obviously the most very basic experiment, which wasn't known until there were landers, is you go there and you just look around with a camera. And do you see a field of grass, or do you see a little creature coming up to you and smiling at the camera or something? And obviously that wasn't what was seen. And then there's the question: well, are there microorganisms in the soil and things like that? And that's less clear. And in fact, in the experiments that were done in the 1970s, I guess, early 1970s, one of the sort of the top experiments was you feed the soil sugar and you see whether it metabolizes, because that's what life on Earth would do. But that probably isn't a very abstract definition of life, because it wouldn't take much of a sort of a shift in how life works to end up with something where you feed it sugar from Earth, with carbon and hydrogen and oxygen and so on in it. And it's like, that's disgusting. I don't want that. Feed me something with, bromine and silicon and something in it, and that will be interesting, so to speak. I was amused. I was looking at the imagery from the Perseverance rover a few days ago, and it's, you kind of look at this sort of sandy environment, and you say, that looks awfully like places on Earth. Well, we have this nice neural network that was trained on basically maybe 100 million tourist photographs that people have taken around the world. and it was kind of trained to recognize where are you when you see this photograph. So I thought, let me feed it the Perseverance rover photographs and see what you get out. And according to that, the Perseverance rover is probably in Egypt or maybe in Saudi Arabia. It's the same kind of look of environment. So that's a potential source for some absolutely bizarre conspiracy theory. But just interesting that the Martian surface really does look very much like what we see on Earth, as far as the kind of the geology of what's going on. The question, of course, is whether at some time in the history of Mars there was the same kind of environment that might have led to life on Earth. And then the question is, if you have that same environment for 1 billion years, will you get life? Or is life on Earth just an incredibly rare coincidence that will only happen one in a trillion times? We don't know the answer to that. One thing you can ask about computational systems is, if you just sort of throw things together and you just see, will this system do computation? One of the discoveries in my life has been this thing called the principle of computational equivalence, which basically says, yes, it will. As soon as you have something where the components aren't sort of obviously simple, they will be able to assemble themselves in such a way, or they'll be able to be used so as to do sophisticated computations, so as to do what we might consider to be abstract, lifelike computations. So it's not a high bar to say that you've got to be able to do these sophisticated computations. Now, the question would be, can you get some specific property like self-reproduction? How complicated does the initial configuration of these computational things have to be before you see self-reproduction? And the answer we know in some systems is, well, yes, it's kind of complicated. It's like 1 in a trillion cases or something. You get self-reproduction. I've actually been looking for a particular system. It's a very simple system that involves just rewriting strings of characters. It's a system that was first looked at 100 years ago, actually. I was just looking at it recently. Since it's been 100 years, I figure one should check it out again. And I've been looking for sort of unexpected behavior in the system that involves sort of iterating these strings. And I found cases, basically so far, every case I've looked at, the thing eventually just dies out. But sometimes it takes a really long time. Like the record holder so far is something that takes about 10.7 trillion steps to die out. But eventually, I'm pretty sure there's going to be one of the things that doesn't die out, that is sort of has a kind of spark of life in some sense to it, and is actually going to keep going and is going to grow forever. I haven't seen it yet, but I'm pretty sure it's going to exist. And that's sort of like a metaphor for the origin of life on Earth. It's like most of the time, these molecules don't do anything interesting, but just occasionally they form into something more exciting. And if you keep going with that, eventually you have a good chance to form these bigger molecules, et cetera, and to form, as I say, it's not a high bar to do sophisticated computation. It's a higher bar to ask for some specific property, like some particular definition of self-reproduction. Okay, so there are a number of other questions here. There's a question here, can there be life inside a solid? Well, it depends what you mean by life, as I was just explaining. One of the things that I think is sort of interesting about different systems, and when we talk about intelligence and life and so on, timescales can be very different. I mean, when we say, do plants have sort of thinking-like behavior? Well, at some level, they have some kinds of behavior like that. Sunflowers turn towards the sun, plants will react to different things happening, but the timescales are vastly slower than what we're used to in standard brains with neurons and electrochemistry of brains. Plants have electrochemistry too, but it's a lot slower. And so that's a case where you can have things that are sort of maybe lifelike behavior, but happening on timescales vastly slower than the ones that we're used to. And that could happen, I think, in solids. In terms of whether, for example, one of the things about the Earth is that life gets everywhere on Earth. You find life in the, where it's very cold, where it's very hot, where it's very high pressure, where it's et cetera, et cetera, et cetera. Life is very broadly distributed. And we can see, for example, with our enemy, the virus, that's an example of how these little tiny virus particles, 100, a tenth of a millionth of a meter size virus particles. They get everywhere. Actually, one of the things that I was curious to work out recently is if you take all the virus particles that have infected everybody on Earth, you just collect them together and you try and put them in your hand, for example, how big is the collection of all the virus particles that have infected everybody on around the Earth? And the answer is really small. These virus particles are tiny, and the number that are involved in infections is large, but not that large. And I think you can pretty much fit all the virus particles that have caused all this trouble over the last year or so in one's hand, so to speak. If you just collected just the virus particles, you just squashed them all together, they'd kind of fit in your hand, which is kind of a sign of just how successfully something that small can get around, so to speak. But anyway, one of the questions is, if you look at the Earth and you say, where isn't there life? Of the chemistry of life that we have, where has it not managed to get? Well, there's a limit to how high it's managed to get. It's gotten right to the bottom of the oceans, so it doesn't really have a problem with pressure in that liquid phase. It's gotten some distance into things like hydrothermal vents. Volcanoes, I don't think it gets that deep in volcanoes. And another question is, if you drill down, is there life deep underground? And the answer is no. It goes only to some depth. There isn't, so far as we can tell, life, at least of any kind that we recognize, that's sort of terrestrial chemistry. How that works with, we don't think there's life sort of deep underground. So that's a place where life hasn't managed to get. Okay, there's a question here from Soap444. Will it be possible in the future to create an atmosphere on a planetary scale? Oh, that's an interesting question. I know my friend Elon has a long-term hope that you can terraform Mars. I think his one of his best schemes involves, you detonate a bunch of hydrogen bombs on the North Pole of Mars. And as I once pointed out to him, if there ever was life on Mars, you just destroyed it if you do that. So you had better be sure that there wasn't anything, that you're not going to be upset that, the archaeological remains of life on Earth are gone forever. You just blew them up. But yes, I don't know whether it would really work, but that's a potential strategy, is to get the kind of water, ice, and so on from the ice cap of Mars and sort of push it up into the atmosphere. And that's a possible strategy. Again, I don't really know if it works. I think all of these strategies that involve sort of majorly changing the atmosphere of a planet, the obvious planet that we might care about trying that on is the Earth. If we're worried about how industrialization, puts carbon dioxide into the atmosphere, well, there are lots of chemical processes and other things that can remove carbon dioxide from the atmosphere. Whether we have the nerve to try them is not so clear. There are one that was for a while popular is to get the plankton in the oceans to be, which use up carbon dioxide, to just get more plankton in the oceans and put, for example, iron into the Southern Ocean to seed the production of plankton there. And that became a big discussion about, who gets to decide whether somebody can just go and take a boat into the Southern Ocean and dump a bunch of iron there and grow a bunch of plankton, which will have presumably some effect globally on the Earth. What are the rules about doing that? Because the law of the sea, which kind of governs kind of what can happen when you're away from kind of the territorial waters of different countries, it didn't really have a clause about dumping a bunch of iron in the ocean. But I think people got all upset about that. And then another scheme is there's a mineral called olivine, which happens to be rather thematically happens to be green, but it's a very common mineral. And it's certainly said that if you put olivine onto beaches and you let it interact with seawater, it will again ingest carbon dioxide and so on. So these are strategies for kind of changing the atmospheric content of for the Earth. Now, another good target might be Venus, and which has a very, surface temperature, maybe 350 degrees centigrade. It's hot enough that there hasn't been a spacecraft, that the spacecraft that land there typically melt in a small number of minutes, like 15 or something. And there's the big challenge of having a spacecraft there. Actually, one kind of interesting issue is if you want to put a computer on Venus, it's really hard to have computers of the kind that we're used to with silicon and so on, working at 350 degrees, if that's right, centigrade temperature. Even if they didn't melt, they're still, the way that semiconductors work just doesn't work at those temperatures. And so the question is there any form of computing that we sort of know how to set up that does work? And it's a rather amusing fact that sort of the mechanical computers of the kind that, like, Charles Babbage imagined in the 1840s and things, those mechanical computers with the right kinds of materials in them would work on the surface of Venus. And so there was being kind of a project to try and figure out, can you make a mechanical computer that's powerful enough that it's actually useful, that will operate on the surface of Venus? And maybe can you even make an imaging system, a camera-like thing that can work in sort of that very high temperature environment in a sort of mechanical computer kind of way? It's a funny and interesting problem. But in the case of Venus, there's again this question of, is it possible to terraform Venus? Is it possible to, for example, put microorganisms in the clouds of Venus to do various kinds of things? And microorganisms have this good feature that if they're in a happy environment, they will reproduce themselves. They'll self-reproduce. So you only have to put a small number of them there, and you'll get more and more of them, so to speak, if they have the right nutrients and so on, as opposed to having to sort of dump lots and lots of them, all that will be needed there. But I think it is not yet known whether it will be possible to do something like terraform Venus. It's going to be an interesting decision point of, you've got a planet, it's been doing what it's been doing for the last 4 billion years. And it's like, okay, we now have the power to, flip the switch, send the spacecraft, terraform the planet, make it into a new, new resort planet or something. Do we do that? Interesting question. But in any case, when it comes to planets around other stars, it's going to be a really long time before we get to find out what can happen with those other planets in our solar system. It's by the time you're much further away from the sun, a lot. I think to have things happen on the timescales that we're interested in is probably not easy, and it's probably not easy for Mars or Venus either. But it's a little bit more plausible in those cases. Okay, let me see. Bunch of other questions here. Let's see. Okay, there's a question here. There's one that's, okay, I'm going to do one that I think is pretty easy, famous last words. And then I'll do another one that's a bit more difficult. There's one from Sarah. Why can electromagnetic waves travel in space while sound waves cannot? Well, the reason for that is that sound waves are, what is a sound wave? When I talk, what's happening is something is vibrating in my vocal tract, and it's creating a wave of pressure. It's making, it's compressing, expanding, maybe a few hundred times a second. It's compressing and expanding the air. And what happens when you compress and expand the air at a particular place, that compression and expansion will radiate outwards. When you compress and expand in a particular place, you'll get this wave of compression and expansion that will expand outwards. You can direct it in a particular direction. If you just have something where You have a little thing compressing and expanding, the wave will go out spherically in all directions, but you can also sort of arrange for it to go in a specific direction. But so what's happening is you have all these molecules in the air and they're all bouncing around. And when you are making a sound, you are making a bunch of those air molecules be closer together, further apart, closer together, further apart, maybe a few hundred times a second. And that's so the sound wave is carried by the air. The sound wave is created by the succession of compression and expansion of the air. And that's what sound is. It's this sort of this kind of periodic compression and expansion of the air. And when you have, for example, a stringed instrument, let's say, you're plucking that string and the string is vibrating back and forth. And as it vibrates, it's producing compression and expansion of the air. And the sound wave is the sort of transmission of that compression and expansion through the air. Electromagnetic waves, like light, don't work that way. People thought they worked that way back in the 1800s. They imagined that light waves would work a bit like sound waves, and that there would be an ether, usually called in a very Victorian kind of way, the luminiferous ether, the light-carrying ether. And people imagined that was how light would work. Turns out it isn't how light works. And that was kind of what led to Einstein's theory of relativity in 1905, was an experiment done in 1900, the so-called Michelson-Morley experiment, which was an experiment to look for what's called ether drift. If something like sound is carried by the air, if you move relative to the air is always stationary, but you can be moving relative to the air. And so you will sort of encounter the sound in a different way because the air is stationary and you're moving relative to it. In the case of electromagnetism, there is no such effect. What happens is there's no sort of stationary ether through which the electromagnetic wave is moving. The electromagnetic wave is moving in such a way that it doesn't. It's just electric fields and magnetic fields that are such that they're not carried by anything. They're just things that exist, and they have the feature that, for example, here's an experiment, sort of a thought experiment. If you have a flashlight, the flashlight is producing light. The light is going at the speed of light away from your flashlight. Okay, now let's say you run very, very fast with your flashlight. Let's say you run at half the speed of light with your flashlight. How fast is the light coming out of your flashlight relative to, for example, somebody who's standing still? You might say, if it was that, well, it must be 1.5 times the speed of light because you're moving at half the speed of light, then the light is coming out of the flashlight at 1 times the speed of light. So the sum of those two things is 1.5 times the speed of light. But that's not what's observed. Instead, what's observed is that it comes out of the flashlight at exactly the speed of light. That's the speed of light is a constant, and you can't make something that goes faster than the speed of light. And so what Einstein realized was that the way that you sort of bring all this stuff together is, yes, it's true that electromagnetic waves always go at the speed of light. To make that work, you have to redefine the notion of length and time to coincide with having it be the case that light has a constant speed. Okay, well, let's fast forward 100 years, 120, 115 years now to our physics project, because we now have a much clearer idea, I think, of what the underlying structure of space is. And so we can ask these questions like, what does light look like with respect to our underlying structure of space? And in our theory of physics, there is something a little bit like the old ether, in the sense that space is not something that just things get placed in. Space is actually a thing itself. Space consists of this large number of atoms of space that are all connected in this complicated network, and that all get updated and their connections get changed and so on. And the progress of time is that progressive sort of rearrangement of the connections in the structure of space. Well, so this is something where when you have a photon, a particle of light, it is actually, in our models, one of the things that's kind of a little bit bizarre. It is made of space. Everything is made of space. What's happening is that things like photons are just particular kinds of structures that exist in all of these connections that make up space. If those connections are just sort of in their ordinary form, then they just make space. But if they have a special structure, let's say they were sort of all tangled up in a knot, then that kind of knotted structure is sort of a persistent kind of structure, and that's what corresponds to things like photons and electrons and so on. We don't yet know precisely how that works, although every week we learn a little bit more about it, and we're getting close now, I think. In that kind of setup, why is it the case that there isn't something like the ether drift in our models? It's a little bit complicated, and it has to do with the fact that, so by the way, in our models, the photon, as it moves through space, basically what's happening is that the photon corresponds to this sort of place where space is a little different, where the connections are a little bit different than they are other places. And that place where the connections are a little different, as time progresses, that place moves a bit. And that moving a bit is the motion of the photon relative to the background of space. And so what ends up happening is you can ask questions like, why is the speed of light constant, and so on. And the answer is a little bit brain twisting. The answer has to do with the fact that when we think about observing light, we're not thinking about it as being outside the universe. We are part of this whole network of space. Everything is made of space, and we're part of that story. And so what you have to think about is, what does an observer who is themselves part of all these updates that are happening, how does that observer observe the things that are happening with the photon? This is one of the things I figured out in the 1990s, actually, about these kinds of models, is that the way that the observer observes what's happening is such that they will always conclude that relativity is correct. They will always conclude, because in a sense, they are trying to perceive updates in the network, but the only updates they can perceive are ones that sort of are affected, that affect the updates that happen inside them. It's kind of the only thing they can perceive is this network of causal relationships, what causes what in the universe. And it's a slightly complicated story, but basically the fact that one is looking only at this network of causal relationships is what gives one the constancy of the speed of light and the validity of relativity and so on. But the answer is, the original question was, why does sound not propagate in space? Well, the answer to that is because there's no air, there's no compression and expansion to make waves in. Now you can ask a more difficult question. You can ask, well, what about propagating waves in the structure of space? What about in this kind of model where we have all these connections in space and so on? What about a wave with respect to compression and expansion in those connections in space? Actually, in the sort of theory of gravity from 1915, Einstein's general theory of relativity, that has the idea that space can have curvature in it. So in both of these kinds of models, you can have, in both our recent models and in the original general relativity model, there's this idea that there can be things happening in space. So the question is, are there compression expansion waves in space? And the answer is yes, they're gravitational waves. And we didn't know for sure they existed until they were detected about 5 years ago in the LIGO experiment, which observed the very intense gravitational waves, the very intense sort of ripples in space that were produced by the merger of two black holes about a third of the way across the universe. And in fact, the details of how sort of the compression expansion in space works are a little bit different than the details of how that works for a sound wave. It's so-called quadrupole deformation, as opposed to it being sort of compression expansion, you talk, and there's compression expansion right in front of where the sound is going. In the case of gravitational waves, it's kind of squashing up sideways and up and down, like a kind of a tidal deformation of the Earth, as sort of it's squashed in on one side and pulled out on the other. So it's a little bit different, the details of how the waves work, but gravitational waves are the analog of sound waves in space. in the sense that they are the compression expansion, in some sense, waves that propagate through space, and they propagate at the speed of light, so far as we can tell, and I think that's going to be true in our models as well. Actually, it's an interesting question whether there are corrections to that. It's an interesting question in certain cases in our models, because it's interesting to see where there are deviations from what you expect from general relativity. In the case of our models, whether you can tell that what's really going on is all of this stuff with updating networks of connections between atoms of space versus the kind of usual mathematical formalism. But anyway, that was a long answer to the question of why aren't there sound waves in the vacuum of space and so on. Let's see, there was a question here about so many questions. Let's see. There's one just came in here, which I'll just mention. So RJ asks, could the physics project predict a phenomenon that can't be observed by humans, but would be faster than light? Actually, I figured that out a couple of months ago. In our models, kind of interesting. There are ways to go faster than light in our models, but they're very subtle and we probably can't implement them. But it's interesting how it works. Essentially what happens is that, what does it mean to go faster than light? It means that you can have an effect on something that's somewhere else in space, and that effect can happen after less time has gone by than you would expect based on going at the speed of light. So just to unpack that a bit. What matters is the relationship between where you can have an effect and how long it takes to have that effect and how far away you're having that effect in space. Well, the point is that because space is this giant network and so on, it isn't precisely kind of a uniform thing where you can just say, this is how far away you are in space. How far away you are in space depends on, in detail, whether you follow this path, that path, the other path in this network. And so what can happen is that you can have this sort of effect that's going out, but when you try to say, how far did that go in space? There are ways to find, there are ways to have that effect sort of go through kind of a tunnel in space that lets it go further than you would expect just based on the overall structure of space. So it's a little bit like what happens, you can think of these atoms of space as sort of, they're not really bouncing around in the universe. They're connected in these complicated networks which are being updated, but it's a little tiny bit like gas molecules bouncing around in a room. And you can ask the question, if I want a particular gas molecule to go from here to the other side of the room, how long is that going to take? Well, your typical gas molecule takes a while, because the gas molecule is going to hit another gas molecule, goes a very short distance, hits another gas molecule, hits another one, hits another one. It does this kind of random walk to the other side of the room, and that's a pretty slow process. But if you were able to figure out exactly where all the gas molecules in the room are going to be, you could pick the exact right gas molecule. And when you're about to collide with another gas molecule, you kind of kick yourself a little bit and say, I'm going to collide with a different one instead. And you can kind of navigate your way gas molecule by gas molecule, and then you can beat by a lot the speed that you would get just based on sort of the natural diffusion of stuff in the room. And it's the same kind of thing in space. If you could figure out enough what's happening in all these little connections in space, if you could figure that out well enough, you could sort of pick the right pieces of space to go through to get to where you want faster than light can get there. Now, you might not be able to get a very big thing through there because you're kind of hacking space to be able to make this little tiny tunnel, or to be able to find this little tiny tunnel that instantaneously exists and go through that tunnel. Okay, let's go find another tunnel. Let's go find another tunnel, and so on, and go through this sequence of tunnels to kind of get further in space than you would be able to do as a photon, as a big sort of particle of light. Well, that problem is kind of a problem both in terms of being down at the scale where you can actually understand individual pieces of space. It's a problem being at that scale. It's a problem perceiving what happens to those little pieces of space, because in order to perceive them, you need some sort of sensory device, and that device is going to be very big compared to those individual sort of atoms of space, because it too has to be made of those atoms of space. And there's also the problem of computing, figuring out, okay, I've got a trillion atoms of space, and I need to know what's going to happen with all of these. And I need to know it faster than it happens in the actual universe. Well, you're embedded in the universe, so it's tough to know what's going to happen in the universe faster than the universe figures it out. It wouldn't be, if it was the case that the universe was sort of wasting its time, if the universe was doing a computation where you could say, oh, well, universe, you just did that very complicated computation, but I have a way to jump ahead and figure out the answer much more efficiently than you silly universe did it, then you might be able to figure out what was going to happen. But we kind of believe that the evolution of the universe is computationally irreducible in the sense that there isn't a way to kind of jump ahead and see what's going to happen. Okay, so I think there was maybe one more. Oh, there's so many. Lots of interesting questions here. There was one from Jonas here about low frequency electromagnetic waves from giant ultra low frequency electromagnets. Could they be sent and detected from giant coils and so on? What happens is the electromagnetic waves, which includes radio waves, are produced by moving electric charges around. So in a typical antenna, like in your cell phone, there's an antenna that goes along the side of your cell phone, and maybe sometimes another, depending on which frequency band you're using. There are also ones that are sort of a bigger antennas, but more or less it's the size of the antenna is roughly the size of your cell phone, and sometimes limits the size of cell phones that make sense to make because of the frequencies of the radiation that they need to produce. But in any case, the way they produce radio waves is by electrons basically being accelerated back and forth, about 1 billion times a second inside the cell phone. And when you kind of have them go back and forth over that kind of distance, you're producing electromagnetic waves whose wavelength is roughly the distance that that's in the cell phone. Well, if you have much bigger antennas, you can have much lower frequency electromagnetic waves. You can have electromagnetic waves that, for example, are down at, for example, 1 hertz. So cell phones might be at 2 or 5 gigahertz. Let's say 5 billion. I was going to say 5 billion sort of peaks of the electromagnetic wave per second. 5 billion kind of changes of direction of the electromagnetic wave per second. So, but you can have things, if you have a big enough antenna, you can have like 1 change per second. Why does one care about that? Well, it's kind of interesting because waves of that low frequency can, for example, go through oceans. They can go through the earth. Waves of higher frequencies tend to go only through kind of free space. As you get to higher frequencies, it's more like light, where it's easy to stop light by just having a piece of solid, for example. And that's why, for example, 5G telephony, which tends to use higher frequencies, is more line of sight. It's more like you have to have a repeater that picks up the radio signal and retransmits it, because it can only transmit the radio signal sort of when it has when it can see where it's going, so to speak. Anything that stops light will also stop those radio signals, and a solid object will tend to stop them. But with ultra low frequency, it can get to the point where you can even have it go all the way through the earth. And so, for example, if you have a submarine that's prowling around under the ocean and you want to communicate with it, ordinary radio doesn't go through hundreds of meters or more of seawater. It gets stopped by that. But ultra low frequency radio does go through that. And so you can your submarine can get can receive radio transmissions that are sent from this very low frequency. Now, one of the issues is that the submarine itself has to have a very low frequency radio antenna, and the submarine isn't long enough to have an antenna that just stretches the length of the submarine to be able to detect those really low frequencies. So it tends to be the case that submarines trail these wires behind them that go a couple of kilometers or more that detect these things. I don't know exactly how it works. I'm sure it's very secret. But you have to make sure that you don't end up with a wire that floats up to the surface and has a bunch of seagulls sitting on it or something like this, because that's a dead giveaway for where your submarine is. So for example, in the US, I believe there's a large antenna in Wisconsin that is an antenna that's used for communicating with submarines, for example. And it's kind of remarkable that that's possible, but it's a consequence of the fact that those very low frequency radio waves can propagate through, for example, through the Earth and get everywhere. All right, I think maybe one more. Let's see. There's a question here, I thought. That I had noticed before, that I thought would be interesting to address. Oh, here we go, from Lewis. Do you think AI-based government and regulation of the economy will be a reality in this century? All right, this is a very different kind of question, but let's address it a little bit. So, one of the interesting things about sort of the history of government and politics and so on is that, in a sense, different things have become possible as a result of different technologies and different kind of states of development of society. So, for example, I don't know, 500 years ago or so, widespread literacy became common in many places around the world. And that made possible certain kinds of democracy that hadn't been possible before, because people could, yes, it's meaningful to make a vote and so on. Then also sort of communication made it possible to actually collect up the votes, deliver them somewhere, have it all be sort of integrated in some way. So an obvious question is, as we have a more sort of computational infrastructure for the world, with lots of technology that didn't exist before, what becomes possible now that wasn't possible before? So one of the obvious things that becomes possible is kind of the use of sort of AI, of artificial intelligence, to determine things about what's happening to determine things in the world. And one can imagine something where, for example, one of the issues would be who sets the interest rates for central banks? If, because that's what determines, when central banks at least believe with sort of modern economic theory, and it actually seems to be working surprisingly well, that they can have some control over what happens in the economy, and that they can control things like inflation. They want a certain amount of inflation, so people just don't sit around and collect and sort of store money, but they don't want too much inflation, or people are not motivated to do certain kinds of things. So they want some number of percentage points of inflation. And the question is, can you control that by controlling sort of the rate at which the central bank of a country will lend money to other banks, which lend money to people and so on? And the question then is, what's the optimal way to pick those those interest rates and so on? And right now, that's done by people sitting around thinking about it, et cetera, et cetera, et cetera. But one certainly wonders, will there come a time when an artificial intelligence that's getting all these signals from all different things and that's monitoring all these different kinds of flows of money and all this kind of thing, and monitoring what all these people are doing and so on, maybe it can make a better decision. Maybe it can make a decision that is sort of more successful at achieving some particular objective for the economy than the people doing it. Now, of course, one of the big issues there is, what objective do you want to achieve? And that can be very hard to define, and people might not agree on what that objective should be. And so that's the issue. Even if you could have that absolutely perfect, amazingly sophisticated AI that's doing this, what do you want it to do? Another issue is this phenomenon of computational irreducibility, that you set up the rules for something and then you say, what's going to happen? And the answer is, there may be no sort of way to predict what's going to happen. You kind of just have to try it and see. And that in sort of the practical world is kind of this law of unintended consequences, that even if you do one thing, it has the unintended consequence that you didn't foresee of something else happening. I mean, when you write computer programs, the unintended consequences story is the story of bugs in computer programs. I thought my program was supposed to do this, but I didn't notice that in this weird case, it will do something completely different that's completely wrong, and that's a bug. Well, you can have bugs when you set up systems of regulations, things that you try to do in the world. You can end up with these strange sort of things that happen in the world that are an unintended consequence of something that you set up. But I think one of the things that is perhaps interesting here, the question of sort of can you regulate the economy using in a more sophisticated way, kind of using sort of modern AI technology. So a little bit of that has to do with a little bit about the theory of money and the theory of value and so on. Because in a sense, it's sort of surprising that money works. What do I mean by that? People are just hanging around and somebody has some sheep and somebody else has some goats. You can say, I'm going to swap some sheep for some goats. I'm going to get some barley in return for this cow, et cetera, et cetera, et cetera. You can have all these different forms of barter happening. But what money does is it says there's this single scale of value, that all these different things, sheep and lambs and goats and cows and corn and I don't know what, education and this and that and the other, they all can be conflated together and they all can just be given dollar values. They can be sort of on a single scale. You can, you can use the money to buy an ice cream, or you can use the money to take a class. And it's not self-evident that there can be sort of a single quantity that can readily be used as a sort of medium of exchange for both ice cream and education, so to speak. But it turns out that there is, and it's sort of a universality property of some kind about the way things work, that it's possible to have that sort of scalar notion of value. Now, there are many sort of mysterious features of what that value actually is. I mean, there was a time when people said gold, it really has value. We're going to, worst cases, this ice cream is worth this number of, I don't know, micro ounces of gold or something. Worst case is there's a true repository value and it's gold. Some other societies had other repositories of value like cowrie shells or whatever else. But people had some notion of it's this thing, it's really has this fundamental value. And I think it was one of the observations, I think Marco Polo was the one who noticed this when he traveled to the Orient from Europe, discovered that they had paper money there. And he's like, this is like what the alchemists are doing. The alchemists, sort of the early versions of chemistry, have been obsessed with the question of, can you turn lead, a very cheap and almost worthless metal, into gold, a very valuable metal? Could you turn lead into gold? And I think Marco Polo referred to paper money as an alchemy of money, because it seemed like you were getting value in this way that didn't have anything underneath it. There was no gold. There was no gold bar that had sort of true value that you could pick up and do things with. It was something where the value was somehow associated with this piece of paper. And how could that possibly work? And obviously more was understood about how that could possibly work and the importance of governments and things in the maintenance of value of pieces of paper and so on. But now, of course, along come cryptocurrencies, and like Bitcoin and Ethereum and so on. And they don't have that same kind of government behind them. They just have a bunch of rules about how you can do things. And in fact, very bizarrely, in the case of these, the sort of first generation cryptocurrencies, at least, the analog of gold, the analog of something that has hard value, turns out to be sort of computational work, which actually is possible. It's possible to have sort of real value through computational work because of this phenomenon of computational irreducibility. And I have have a high suspicion that the inventor of Bitcoin was very aware of my work in computational irreducibility, and that was kind of this way of sort of establishing value by just doing computational work. Now, in practice, that means, as people may know, that there's this bizarre idea of Bitcoin mining, in which you have, a special purpose computer that can do a large number of gigahashes, a large number of these mathematical computations per second, and if you can with using a lot of computer power and electric power to power your computer and so on, you can get at a tiny rate at this point. You can just create value from nothing. It's like going and digging gold out of the ground and spending lots of effort doing that. But there seems to be a notion of value that is independent of any of the sort of base value of having something like gold or computational work done that way. It's some kind of notion of value that's associated with just the pure network of transactions. And it's an interesting question whether it's necessary that you still have, in the case where you have a more sophisticated kind of network of transactions, which you can understand more clearly, do you need to have only this kind of single scale of money? So, for example, if you look at the prices of things in today's world, it's very common to say, well, this thing is $10. Okay, great. But also, there are some things where the prices are complicated and dynamic. For example, airline tickets. That's a case where back in the day, it used to be there was pretty much a list price. You paid X number of hundreds of dollars for this plane ticket, etc. But in more recent times, it became something where there's very detailed sort of auctioning of plane tickets based on the specifics of how many people want to go at this time, et cetera, et cetera, et cetera. And it's very dynamic pricing. Even more so with ads on the web, where the dynamic pricing happens in hundreds of milliseconds. When you look at a web page and those ads are loading in, somebody is bidding on those ads. Different companies are bidding to say, I want to show that person this ad. I want to show that person this other ad. And that's all happening electronically in a sort of computational marketplace. So a question I don't know the answer to is, in sort of a computational view of money, is it the case that this old idea of things have a price and there's just one price might just go away? And it might be true that sort of almost everything works by sort of transacting dynamically between different things to know, oh, well, that ice cream is going to cost a little bit less because we had already opened the freezer to get this thing out of it, and we already, chopped up half that banana, and so it's going to go to waste if it's not used in the next 10 minutes or something. And so the ice cream is going to cost a little less. And at a point where there are sensors that are kind of sensing everything that's happening in the world, and at the point where sort of the effort of figuring out prices is free because it's all being done by some AI, it becomes possible to think about doing other kinds of things in terms of those sort of economic transactions. I mean, if you were going to work out, I'm going to change the price of the ice cream because I already opened the freezer, way too difficult for people to figure that out. It's not worth it. It's better to just say it always costs $2 or something. It doesn't matter what, whether the ice cream was the back of the freezer and you had to go and fetch it, or this or that or the other. It's always the same price. But in a world where basically the people who are buying things have AIs doing the buying for them, and the people who are selling things have AIs deciding on prices for them, it becomes a slightly different situation, and it becomes something where you can imagine sort of deviating from this notion of just the scalar price, so to speak, just the single number that represents price. So it's sort of a curious view of the future of an economy to imagine all of these different sort of dynamic prices happening in different places. if it worked that way, it is deeply based on AI, because it has to have, all those different decisions have to be made automatically, for each individual sort of situation and agent in the whole picture. Now, in the case of, in that situation, you say, well, what are the big levers that, for example, a government could use to control the inflation rate? When all these microtransactions are happening and they're all being done with dynamic pricing and so on. Like, for example, people try and assess whether there's inflation. What does it mean that there's inflation? Well, normally it would be, well, this thing that usually costs $100 is actually now going to cost $120. And that means the value of $1 has gone down because I got the same bucket of stuff, but I had to pay $120 for it instead of $100 for it. How do you assess that kind of inflation? So what's done in practice is, for example, is to create this thing called the Consumer Price Index. And the Consumer Price Index, it's a little tricky to create it because you have to say, what should be in there? Are you buying, orange juice? Are you buying gasoline for your car? Are you buying housing? What are you buying? And you have to have sort of a basket of things you're buying, because different people will buy slightly different things. And so the cost of living for different people will be somewhat different. And over the course of the last, 100 years or something, the kind of what's the mix that has been used to determine these cost of living indices, the Consumer Price Index and so on, has changed somewhat. But that's, so now the question is, and even to assess inflation, even to measure inflation, you have to have this kind of Consumer Price Index. You have to say, okay, things are more expensive in the sense that you're spending more dollars to get the same stuff, but what stuff it is affects whether you come to that conclusion. Like, for example, it could be the case that real estate in the middle of a city is getting more expensive because there's a limited amount of it and the city is very built up. Or it could be that consumer electronics is getting cheaper because it's getting cheaper and cheaper to manufacture something because there's larger scales. So it's a complicated thing to assess that. And in a situation where you have a lot of sort of independent, dynamically priced microtransactions happening, the question of what is the actual sort of Consumer Price Index analog, that will be a complicated question. And if what a government does is just move the big lever and say, change the interest rate, that will be a very coarse way to do things. Now, what the government could instead do is say, okay, we're going to change some detail of the AI algorithm. And ultimately, one of the big things that governments do is taxation. They levy taxes. And the question, the US tax code, for example, is a very complicated thing. And, I notice, I guess it's almost tax filing time. And back when that used to be on paper, somebody like me has a very thick pile of paper for their tax return. And, that's because the rules are very complicated and detailed, and, they involve this and that particular thing, and there's an extra piece of paper for that, and there's a thing for this, and so on. And so, those tax rules have been tweaked to achieve certain objectives. And people don't necessarily agree on the objectives. And, as the political climate changes, the detailed objectives change, and some detailed different thing is changed in the tax code, or the percentage rate of some tax is increased or decreased, or increased for this size of income or whatever else. And so there's one of the things that governments do have control over is how taxes should be levied. And one can imagine a situation where, right now, taxes already have a very complicated algorithm that determines what they are. But one can imagine a situation where that's even more complicated, and where it's even more dynamic, and where, when you buy that ice cream, the sales tax is dynamically computed based on whether it was more or less expensive to do trash collection in your city that week, and things like this. Stuff that you couldn't imagine doing right now because it's way too difficult to set those prices. But where if everything was done at sort of the level of AIs, it becomes much more possible to imagine that all those things are set dynamically. And so then you have this interesting situation that, the tax code becomes this piece of genuine code that really is a dynamic running piece of computation. And that's an interesting situation, and one wonders what would happen in that case, because then, it is already true that sort of a bug in the tax code can have weird consequences. Like when I lived in England, there was some tax write-offs for, I think, for racehorses at one time, and then everybody was buying racehorses, which wasn't really quite the intended consequence of some detailed thing in the tax laws. Or, people are like, I don't know, in England, perhaps there was more, maybe not more complexity, but more propensity to game some of these things than perhaps in some other places. But all these weird things people do in order to sort of drive through these kind of loopholes created by unintended consequences of things like the tax code. But it becomes a much more complicated story when that's sort of all being run by AIs. But then the ultimate question is, what do you tell the AIs to do? Let's say the AIs were actually making up the tax code for themselves. They still have to have some kind of constitution or contract that tells them, okay, what were you trying to achieve? In this tax code, what did you want to have happen? And there has to be a description of that. And that itself is kind of a code that defines the goals for the AIs. There's a case of this that's happening right now that I've been a tiny bit involved in, which is the case of sort of selecting things like news content or search content for people on the internet. And that's all done sort of dynamically by AIs. And the question is, what were the AIs told to do? And in a sense, the AIs, and it's no fault of them, were told to do things like maximize ad revenue, put up those news articles which will cause people to spend as long as possible on the website, and therefore to generate as much revenue from running ads next to that content as possible. So it's kind of a dynamic where the original thing the AIs were told to do on behalf of companies and on behalf of the shareholders of companies and so on was, maximize the revenue associated with producing this news. Well, so then of course the AIs do a fine job, and the AIs discover things like those crazy humans. The more outrageous the news story, the more likely they are to click on it. So let's feed them the most outrageous news stories. The more likely the news story is to agree with what they already thought was going on, the more likely they are to click on it. Let's feed them things they already thought were going on. Let's not feed them kind of the opposite, point of view or something about what was going on. So the result of that is what was originally just show them more ads becomes sort of the unintended consequence of the way to achieve that is to sort of play on various foibles of humans, various details of humans, and to do things like show them this kind of content rather than that kind of content. And of course, there are all kinds of societal consequences to the fact that, for example, different people get shown very different kinds of content and believe very different kinds of things as a result of that. And people are outraged by this and lulled into a sort of sense of security by that, and so on and so on and so on. But that's a consequence of basically somebody telling the AIs to go off and do something, and then the AIs figured out, oh, we brilliantly figured out what to do. It just turns out it has some unintended consequences. And then you can start saying, well, let's add some patches to that. Let's tell the AIs, we really want them to do this, but we want to sort of also have them do a little bit of that. And then pretty soon you've got this very complicated code for the AIs. So in a sense, the way that the world is set up right now, we have systems of laws that govern what humans do, and they sort of directly, in some sense, govern what humans do. And in a sense, what we're saying here is maybe we put in a layer of AIs here, and the AIs are controlling lots of kinds of things in the world, but we also need a layer of laws for the AIs, because in the end, we have to tell the AIs what we want them to do. Because there's no, if you just say to an AI, okay, you're in charge, run the earth, what's it supposed to do? It could say, I really like red birds. I'm going to have, the earth taken over by red birds. Okay, why? Or I really think, it should be the case that, every human should be able to eat as much ice cream as possible. Okay, you can make that decision too. And each one of these things, you can kind of optimize the world to achieve those objectives. But somebody has to, somewhere those objectives have to be injected into the system, because the AI on its own is not something that can generate those objectives. Those objectives come from some sort of outside sense of purpose and so on. And that's something that we as a civilization have developed differently in different places and for different people. But that's, that's sort of a big piece of what we've developed as a society and a civilization. And that's what, if we're going to have the AIs take over, so to speak, that's what we have to communicate to them. So anyway, that was a more complicated question here. I'm just seeing one comment here from Michael. Yeah, he's commenting that basically the AI will end up sort of negotiating with people in the world about what it should do, and that will make the AI very human. The basic point is, in the end, we have to imprint human values, whatever that means, and there isn't a uniform sense of what human values are. We have to imprint our various human values on the AIs. And really the problem is, and actually I hadn't thought about it this way, but it's at a very mathematical level, when you define coordinate systems for things, you'll end up with patches of coordinates. You won't be able to have a single coordinate system that sort of fills a whole surface because the coordinates don't agree and so on. And I realized that if you're defining AI purposes for the world, you have essentially the exact same problem. You can have a region of the world where this set of purposes, this set of human values, great, that works. For this set of people, that works. For another set of people, that works. But they're all fitting together in the world. And so in a sense, what has to happen is the same kind of thing that has to happen when you set up, very technically, things like gauge conditions when you set up coordinate systems in general relativity. I'm sorry, that's an allusion to something rather abstract and complicated. But basically the point is that if you're going to have these different sort of value systems coexisting in the world, I just realized that that's very similar to some questions that come up in sort of distributed computing and in physics about how you sort of fit together different kinds of things that are happening. Because the problem is, if you're in the world as it is, and you say one set of people want to drive on the right-hand side of the road, one set of people want to drive on the left-hand side of the road, okay, how does that work? Because normally, you've just got this one road and you've got to have a decision, which side of the road are you going to drive on? Of course, things get more complicated when everything is run by AIs, because when everything is run by AIs, there's no reason why the cars can't just drive wherever they want. And the AI can sort of use its knowledge and computation to, just negotiate. Cars are in radio communication, they're negotiating with each other. Okay, which side are we going, which way are we going to pass on this road at this time? Okay, it'll be that way. And another time you're kind of using computation. Computation is free. And so these cars can just do this real-time negotiation, just like in the case of prices. All right, lots of interesting things to talk about. And thanks for what gave me kind of an interesting idea there. So I appreciate that. Well, lots of interesting questions here. Look forward to doing this again same time next week. But for right now, I need to go. I need to go attend to my day job. Actually, it looks like we're live streaming the next piece of my day job, which is a review of visualization functionality in Wolfram language. But from this stream anyway, bye for now. Thanks.